The project, as I said, sponsored by California Department of Transportation. The project manager is Charles Sikorsky. He is with Caltrans. And then we have a co-PI for this project, Dr. Matt Rouse, who is a senior lecturer with Iowa State University. And the graduate student who did most of the analysis is Dr. Ebadullah Honavar, who has finished his PhD and joined Jacobs in the New York office as a structural / bridge engineer. Here's an outline of my presentation. So I'll just give you a quick background and define the problem, and then suggest the research objectives, and then I'll get into the deeper into the analysis of the time-dependent effects on post-tension concrete bridge girder, box girder bridges, and then I'll conclude with a few remarks. So from a background point of view, I want you to realize, most of you know that the concrete members are subjected to pre-stress because we want to counteract high internal forces. They are tensile forces and tensile stresses expected due to dead and live loads. Pre-stressing can also minimize deflection of the members as well as improve their shear behavior. When you apply pre-stressing, typically concrete in the member experiences compression, and some parts of the member will experience tension, while the pre-stressing tendon will be subjected to tensile forces. There are two ways to pre-stress concrete. One is pre-tension, the other is post-tension. Here our focus is on going to be post-tensioning of concrete bridges. In this particular case, the concrete will be cast and cured before you apply the post-tensioning or pre-stressing in the structure. The advantage of this approach is that you can have more effective pre-stressing. As you see from the left figure, you can use a curved profile for the tendon to make the pre-stressing more effective. Typically in this case, you are expecting the pre-stressing tendon to be located within the ribs. That's what's shown on the right-hand side. On the left-hand side, it shows where the entire pre-stressing effectiveness is going to be along the length of the web. The time-dependent effects is a focus here, which is the time-dependent effects on pre-stressed bridges. So once you build a structure like this with pre-stressing, the strains and stresses in a pre-stressed concrete bridge will continuously change over a long time. The cause of those changes are time-dependent properties of concrete as well as steel, in this case, the steel reinforcement or the pre-stressing tendon. So typically you will have creep and shrinkage behavior in concrete that will affect the stresses and strain. Often the reversal of the creep is referred to as the relaxation, but they are two different things. In concrete creep, you're applying a constant force and let concrete to creep. Under relaxation, you're maintaining a constant strain, allowing the concrete forces of stress to reduce as a function of time. The relaxation of pre-stressing steel is also expected, and which will also reduce the effects of stresses in the concrete. And then the pre-stress losses resulting from time-dependent effects will also in turn affect the stresses and strains. Thermal effects can also take place, which comes from heat gain or loss due to solar radiation and convection to or from the surrounding atmosphere to the structure, which can also induce stresses, even though we are not focusing, or we have not focused on thermal effects in this particular study. The last point I want to emphasize is that variation in loading and the support location, including boundary conditions, can induce changes in stresses and strains. Typically, the post-tension box girder bridges will undergo different construction stages, and in this particular case, that changes in different stages can also introduce. So ultimately what we are interested is to complete a design of pre-stress bridges with more accurate approaches, understand the time-dependent effects, even though they're complex, we want to be able to use more rational approaches so that we can design them efficiently and account for the design forces more accurately. So that's what we will focus on in this presentation. Okay, let me focus on the superstructure shortening issue as a function of time. So what you see here is a continuous bridge. You have a bridge frame. Superstructure is made up of a continuous box girder supported by 2 columns and then 2 in regions where you have simply supported or supported on rollers. With time, there will be shortening taking place in the structure. Such shortening will not be restrained at the ends, so the superstructure is allowed to move at the ends of the frame. However, at the intermediate supports where piers are restraining the moments, will introduce some restraints to the superstructure moment. So the restraints that the columns have on the superstructure moment is going to be very insignificant because the stiffnesses are small. But if you look at the changes to the stresses in the superstructure, you will see that the superstructure change will introduce a deformation at the top of the column, and therefore that deformation will introduce a base shear in the column and a base moment, and that's what we want to be able to accurately estimate in this case. I will also emphasize that there is a point of no moments. In other words, the point that you see here in this picture is where the superstructure does not move because of the deformation taking place on either side. Let me show you a video of a frame that we built in MIDAS Civil, and that shows a multi-span frame. Typically, the construction of the substructure first takes place, and then you apply the superstructure or you add the superstructure, introduce pre-stressing, and then the time-dependent effects will continue to take place, and which is something you can see in terms of how they deform. So the points to emphasize here is that the extreme columns are expected to undergo much larger deformation than the intermediate columns. In some cases, you may not experience any deformations. You may have roller supports at the top of the columns, or that particular support will not introduce any forces in those columns. But overall, you can see our hope is to figure out the maximum deformation and the corresponding forces in the substructure columns. So the concerns with the current design approach is that we typically use a constant strain rate for the superstructure. So regardless of the bridge that you choose, you may choose a constant strain rate for evaluating the superstructure deformation. The columns are typically assumed to be cracked, so therefore you would use a crack section properties. And then one of the things that we have not given special consideration is that as the column is being subjected to a deformation, which is a constant deformation initially due to pre-stress, and that's going to continue to grow, the forces in the columns will actually reduce due to concrete relaxation. So hope here is to make sure that the relaxation will have some beneficial effects in terms of design forces that will also be captured in the design process. If you don't account for the relaxation, obviously you're going to overestimate the column shear forces. Overestimating the column shear forces will lead to inefficient design of columns as well as the foundation, increasing the adverse effects of the time-dependent issues because you overestimate the forces, you increase the stiffness, therefore the forces in the columns and foundation are going to increase, and ultimately all of this is going to increase the cost of the structure. And then I already mentioned that thermal effects is a possible cause in terms of introducing additional deformation of the superstructure, which should be accounted for if that is an important piece for your design. So our research objective was to improve the prediction of the strains and stress buildup during and after construction, and reduce construction challenges and associated costs due to a use of an inaccurate design approach. And our goal was to achieve the research objective by improving the prediction of time-dependent effects on cast-in-place box girder, pre-stress box girder bridges in a systematic manner. So that's what I'm going to go through for the remainder of the time. Okay, so let's start with the current design practice. So in order for you to estimate the column forces, you need to assume a shortening strain rate. Typically, different numbers are being used by different agencies. I'm showing you 525 microstrain for the superstructure, which is a number that has been adopted in design practice. Then you will figure out the point of no moment that's shown here. And once you know the point of no moment, you should be able to figure out, the strain rate and the point of no moment, and therefore you can figure out the amount of deformation that the column will experience, from which you can calculate the base shear as the product of column displacement times the stiffness, possibly considering the cracking or flexural cracking of the column. The 525 microstrain I mentioned was originally developed based on bearing designs. So for joint bearing designs, some assumptions was made, and this was not specifically designed for the type of problem that we have dealt with, and therefore it's important to verify that number is appropriate. Ignoring the concrete relaxation or assuming all of the columns will crack may underestimate or overestimate the design forces, and that's something we want to make sure that gets captured as well, as accurately as possible. So in our study, what we did was we wanted to capture the relaxation of concrete directly. So typical approach in the past has been you take a creep function and you reverse the creep function to establish a relaxation function. The creep and relaxations are treated as interchangeably, which is not a bad assumption. The research in the past has shown they can be shown, or they can be used interchangeably with appropriate reversal of the function. However, there have also been research published suggesting that the two phenomena are not necessarily identical, and in the past it was difficult to perform relaxation test. It's easier to perform concrete creep test. Creep test has been done over 100 years. It's fairly straightforward to perform a creep test. Technology today exists for us to perform relaxation test directly, so we wanted to do that relaxation test directly rather than doing a creep test and reversing the curve. And then we wanted to examine the beneficial effects of concrete relaxation on a prototype cast-in-place box girder bridge. In this case, our intention was to do a thorough analysis of one structure and make sure that all of the forces that we have quantified or that from the analysis make sense. And then we went and did several other bridges, a total of 8 bridges, to look at different trends, and then from that we developed or formulate our design recommendation. Okay, so let me just start with a first task that we undertook. So it was a relaxation test. We performed this test on 3 different members. 2 are circular reinforced concrete columns. 1 is a circular reinforced concrete beam. The diameter of all of these members were in the 8 to 12 inch range. Specimens are 4 feet in length, and they were loaded at the age between 48 to 150 days. A number of tests were performed using these 3 different specimens. The age of loading will vary, duration of loading will vary. In 5 of the 7 cases, we applied axial compression. In 2 cases, they were subjected to flexural tension. So flexural moment, in one case before the beam cracked, in the other case after the beam cracked. So what you see here is a axially loaded column, which both of them did not have any reinforcement inside. It's just a pure concrete, and we wanted to get a feel for how they perform. The reinforced in the beam, though, we had longitudinal reinforcement and spiral reinforcement, and the the reinforcements also had some strain gauges to capture the change in strain or the strains on the reinforcement during the test. Okay, let me just show you some results that's showing you the observed behavior for all of the 7 tests, and you could see that the variation in the mean applied strains were pretty small, so we kept it constant as much as we can. The thermal and shrinkage strains were kept small, it's less than 10 microstrains. We used a dummy sample to make sure that was the case. And then you can see the stress applied at the beginning of the test and at the end of the test. And the most importantly, you see on the right-hand column, the change in stress due to relaxation varied as much as 49% in one case, the very first test, to 16% in the last test, which was the older specimen. So obviously the older the specimen, lower the relaxation loss in the force or stress is going to be. We then looked at for the different tests. I'm showing you the strains, the stresses, and the strain gauge data as well. So let's just start with the very first figure, which is on the left, which shows the strains were kept constant if you look at the green line, and that was our motive to perform the relaxation test. The black line shows a step function. Purposely, in these 2 cases, we applied the initial stress in steps because this is what a typical column would experience. On a gradual fashion, the strain buildup will take place, but yet one would expect some losses in the stresses because the relaxation takes place. So the left-hand side shows that we managed to maintain the strains as constant as possible. The second figure shows the relaxation losses in the green and red curves. The black curves doesn't quite indicate this is because the actual target line was actually much higher. The values that you see here is after losses, but one thing to observe here is that between each step you can see the drop in stresses, which is because of the relaxation taking place in that member. On the right-hand side, you can see the strains in the last test, which is the beam, where the strain gauge data of beams, the reinforcement shows that strains were kept constant during that test as well. So the relaxation function can be generated using, assuming to capture the reduction in stress due to a unit constant strain. You could use for example, ASH2 recommended creep model, and from which you can develop the relaxation function, and then that information can be established for a more of a time step method as shown here, which will be required in terms of performing a finite element analysis, and that's what we performed in MIDAS Civil. You could use an approximate method proposed by Bazan, or you could use a much simpler approach where you modify the modulus to represent the change in stresses because you're maintaining constant strain. What we did was relaxation functions was established based on the measured test information, and we found a good agreement between the measured test results and the finite element model. So you can see in this case the the red line is the finite element analysis results, and the black line is what we measured during test, and we were able to capture the expected behavior in MIDAS by choosing appropriate relaxation function. In the Bazan model, you could see that the drop is much more sudden. There are ways to improve the Bazan method if you, for example, go and perform this calculation using a much simpler approach. Since we chose to do the analysis using the MIDAS Civil, we relied on the finite element approach to perform all of the analysis in this particular study. The beneficial effects of concrete relaxation on a post-tension concrete box girder bridges were evaluated then in detail using a frame 6. So that's one of the frames of the flatway viaduct that was designed by Cartrans. So let me show you the details of this particular frame. This one has a multi-cell box in the superstructure. The structure itself has a span length of about 259 meters or about 845 feet. It has a circular column, and each bend has 2 columns, so it's a 2-column bend with a pin detail, as you can see here, between the column and the foundation. We also modeled, during the model development, we made a few assumptions. One is that even though the structure had this particular frame is a curved structure, we eliminated and assumed zero curvature. This is to make sure the analysis can be easily interpreted and the results can be used for averaging between different bridge structures that we were hoping to accomplish. We did not include the non-pre-stress reinforcement, and we initially assumed linear elastic behavior for columns, and then we modified the elastic stiffness once we realized that columns have cracked. The material models in the analysis were based on the concrete compressive strength. The time was based on the ACA approach. The modulus of elasticity was assumed using AASHTO recommendation, and the concrete creep, relaxation, shrinkage functions were developed as recommended by AASHTO. We applied the dead load and pre-stressing forces. The moment curvature of the column sections were performed using a subhydraulic section, and the column stiffnesses were evaluated based on the moment curvature analysis, whether depending on is a cracked column or uncracked column. The bridge goes through different construction stages, which I will show you next, and all of these construction stages were modeled in order to capture the changes in stresses and strain accurately. So this figure shows the pier construction. So typically we assumed in this case, with input from Caltrans Technical Advisory Committee, that the substructure construction will take place from 0 to 90 days. Then you add the superstructure from T equals 90 to 180 days, followed by deck construction. So that goes from 180 to 210 days, followed by pre-stressing in the superstructure taking place between 210 to 220 days. And finally, the barrier construction was completed from time 220 to 235. So this is when you complete the structures. At this point, the column has experienced changes because experienced lateral deformations and the corresponding forces have been introduced. The question is how much force was developed in each of the column due to superstructure shortening. And if you look at what we have accomplished in this case, is that the results from the analysis clearly shows that whether you account for relaxation in the column or not, obviously you're going to see noticeable differences in the results. Shortening strain rate of the superstructure was something that you could calculate based on the analysis, and then the variation of column level top displacement as a function of time, and the base shear can also be calculated. So I'm showing you a few different figures. So let me start with the top right figure, which shows different curves. So it shows you the dead load curve, that's the purple line here, then the creep strain, the shrinkage strains, and the pre-stress strain. That's a pre-stress strain. The red curve is the shrinkage. So shrinkage effects is pretty significant in most cases. This is a shrinkage of the superstructure, and then the black line shows the total effects. So if you, for example, looking at a shortening strain rate, a total shortening strain rate of, in this case, 900 plus micro strain is what you're expecting at the age of about 2,000 days, and all of our analysis were performed for time equals 0 to 2,000. The bottom two figures shows the column displacement. The column displacement shows again for dead load, creep, pre-stress, the pre-stress, creep, and shrinkage, as well as summation. You also see in this case two lines, two black lines, which shows with and without the relaxation that the system will experience. The next figure highlights the corresponding forces, and you can see more clearly the base shear forces in this case are such that let me just go back to the previous slide. So this one shows the base shear force in column 26 and column 24, and you could see the different deformations taking place, and the black line gives you the summation of the base shear force, and likewise you see the black line here that gives you the summation. So in this particular case, you can see that the two columns see very different magnitude of forces. So it's one thing to realize. The further away the column is, the higher the forces are going to be developed because the highest deformation on the columns. In the bottom, you see the corresponding moment, and on top of the corresponding moment, I've also shown the cracking moment, the yield moment, and the ultimate moment. So if you look at column C26, in this case, you can see that the moment build up in this case is getting very large and getting closer to the yield moment, whereas in column C24, the buildup of moment is small enough that you're not even expecting the beams, the columns to experience any flexion or cracking. If you go to the next slide, you can see the time-dependent effects on 8 different PCBPs. So what we did in this case is that we understood how a frame in a bridge will perform, and in this case we brought in 7 other bridges with varying span length and configurations. We calculate the shortening strain rate for each of the bridge like we have done for one bridge, and then we evaluated the column top level displacement of the corresponding base shear, and we evaluated the current design practice against the finite element results, and then we developed some simplified approach to make sure that the current design procedure can be improved with a more rational, simple method. So let me share some of the bridges that we have looked at. We've included with Caltrans input small, short, and long span bridges. Pier type included multiple as well as single column bends. The connection type to the foundation, both fixed and pin conditions were used. And then the amount of pre-stressing in the box girder itself also varied in these bridges, and that's how we formulated these 8 different cases. As you can see here, the bridges are labeled from B1 to B8. B1 is the shortest bridge, and then the B8 is the longest bridge. So if you look at the bridge length, it goes from 145 meters. It's, the lengthwise it's not the shortest, it's a 131, it's the shortest. And it goes from 131 all the way to 426.7 meters. Each of the columns were labeled as you can see here. So when I refer to some of the results, I will say in bridge B4, column C12 experiences, you can relate that back to the different structures that we have evaluated. So B1 and B2 are short span, B3, B4, B5 are medium span, and B6, B7, B8 are long span bridges. The details of the box girder bridges are shown here, so there are some variations to observe. The initial axial stress, as I said, that's a pre-stress, is not constant in these bridges. They vary between 4.8 megapascal to 11.4 megapascal. That's the information that we found from the design details of the design drawings. The anchorage set friction coefficients are all specified in the drawings, and same applies to the wobble coefficient. All of these reported values were used respectively for each and every bridge analysis. You can see some examples of the elevations view and cross-section. So this is one of the short span bridge to a medium span. In this case, you can see the frame length is about 231 meters, and the 426 as the longest frame with multiple spans is shown as the third case here, basically giving you a view of 3 different bridges that we have included in the analysis. All of these bridges were designed and constructed by Cartrans, or under construction by Cartrans, and we selected these bridges with basically with input from Cartrans. The bend details, I said different configurations were used. You can see there are 2 cases. We have flared column. In one case it's a spin at the base, and the other case is supported on drill shafts. And here's a single column with the overlooking spirals in the column. In this case, this column is also supported by a type 2 drill shafts. For the analysis, we use the AASHTO creep coefficients and shrinkage strains, and this one shows the creep and shrinkage strains calculated for different bridges. And in each of the cases, once we calculate the strains and creep coefficients, we also looked at the average value. So this one shows what AASHTO recommended value for each and every cases are, and this one shows the recommended values for the columns. And you can see the columns are older, and therefore the creep coefficients variations is smaller compared to the superstructure, where the superstructure creep takes place at very early stages, because the pre-stressing is applied at the age of 7-10 days when the concrete is reaches 7 to 10 days strength, whereas the column has been sitting in the field and maybe as old as 180, 200 days before the constraint is introduced, and that's what you're seeing the difference between the two. This one, let me show you some results of the analysis. So shortening strain rate of the superstructure due to dead load, pre-stress, creep, and shrinkage were evaluated, and then we followed and figured out the column top lateral displacement, and recall that we have also activated the relaxation. So that relaxation is active in these analyses, and what you're seeing here is a 2 of the bridges, B2, B3, along with B8, which is the longest bridge that we analyze. And you can see in these columns, especially the B8, the extreme columns will undergo much larger deformation. The columns close to the center of the span may not experience any significant movement. So as we've seen before, you would expect extreme columns to experience maybe cracking and experience much larger strains, but not necessarily the column in the middle. So making an assumption that all columns will crack doesn't necessarily mean much, because your stiffness of the column will vary. Okay, so let's take a look at some of the results here. What I'm showing here is the different strains develop in all 8 bridges, along with the average you would calculate. And then you also see the total effects that's shown in the bottom right corner here. So starting from the dead load and going at the top is you have the dead load strains and the pre-stress strain. Remember, the pre-stresses are different, so that's why you're seeing different strains. Then you have creep strain as well as the shrinkage strains. As I said, the shrinkage strains are typically much higher. So you can see in this case we have a shrinkage strains of about 575 all the way to about 775 microstrain. The right corner, you can see that the bottom right corner, you see the total strain. So this basically giving you a feel for the shortening strain of the superstructure, and you could see that from B1 through B8 we have a shortening strain of anywhere from 650 all the way to close to 1200 microstrain. So this value is not necessarily constant. It depends on the bridge that you're dealing with. But using an average may be appropriate. Using an average plus some standard deviation may be appropriate for you to establish conservative design process, and which is something we'll look at it. I know we are showing a current practice at 525 strain, as I mentioned before. This is not necessarily correct, because the current practice of 525 subtract out some pre-stress strain as well as some other effects. So we are actually in discussion with Cartrans right now to make sure that we reflect their practice more accurately. But one thing is clear is that in that the current practice does assume a constant strain rate, and you can see that the bridges shows different strain rates based on what we model. So let me move on to the next slide here, which shows the column displacement and shear forces in the same manner. And I'm showing you for different cases. The top figure shows the column displacement, the bottom figure shows the base shear, and in the top I'm showing you on the top left you see the B2 bridge, the B5 and the B8, and the bottom for the same structures you see the base shear forces. So you could see that clearly if you look at the the top displacements or base shear forces, these values are not constant between the columns. The extreme columns typically see much larger forces. Again, you can clearly see that as you get closer to the center, some of these columns see very small forces, and therefore they may not be even experiencing any cracking as much as you see for the extreme cases where the cracking may take place in a matter of days. So from a design recommendation, what we have done is the concrete creep and shrinkage values assumed to stabilize after 2,000 days. So even though we picked the 2,000 days, I will emphasize, going back to the previous slide, that the amount of time-dependent effect that takes place in a short time frame, something like 6 months, is much more significant, and is probably 80–90% of the total effect that we see in 2,000 days. The reason we use the 2,000 days is the number that we collectively agreed with Cartrans as a time by when we assume all of the time-dependent effects have stabilized. So that's the assumption we made. The ultimate condition for the deformation and forces were defined at the age of 2,000 days as well. And then in terms of the current practice, what we wanted to do was to look at 3 different approaches to see which method would work better to improve, and how accurate these forces have to be estimated so that one can improve the design practice. So this one shows the current approach as well as the recommended approaches. That recommended approaches include 3 different methods. I'll go through in detail, but let me first comment on the current practice, where a 525 microstrain is assumed as the superstructure shortening, but that does not include the pre-stressing strain. And as I said, this is the issue that we are discussing with Cartrans in terms of how that should be captured. But let's focus on the 3 different approaches that we have included. You could see, if you look at how the pre-stress is captured, in the first approach we just simply take the axial amount of pre-stress that's been applied divided by the modulus divided by the cross-section of the superstructure will give you some average pre-stress strains. And the creep strain is therefore taken as the pre-stress strain times the creep coefficient. You account for the ultimate or the total shrinkage strains, and you figure out the column forces based on the deformation you estimate. The second approach, we basically use the finite element results that we calculate for each and every bridge, but use a simplified analysis to determine the base shear forces, the top level displacement and the base shear forces. So you would expect this approach to be more accurate because each and every bridge was modeled based on what we learned from the analysis of finite element. The third approach is probably the most realistic in terms of making a recommendation, is that we took the average of the finite element results. So in other words, we have results for the 8 different bridges. We took the averages and we established them as the recommended values. So that's one direction to go. As I said before, we could also include this value along with some plus standard deviation to get some conservative results. But nevertheless, we are comparing these 3 different methods with what the finite element itself predicted as strains. So you could see here that the total strains are compared for, again, the current practice is expected to be lower because the assumption, and we should include the pre-stressing strain here. But if you look at the 3 methods that we're looking at, they actually came out to be pretty close to one another. In some cases, you see that the method 1 and 3 are closer than the 2, but in some cases you see that approach 2 and 3 are closer. And we typically expected approach 3 to be more accurate and maybe approach 1 to be least accurate in relative terms. Probably the most accurate of the finite element would be the approach 2, and that's something that you see the differences. If you look at the ultimate displacement that we calculated for the 37 columns is shown here for the 3 different columns. So in terms of the directions and how we are estimating the displacement based on our approaches. And this one shows the different components. So for example, you have shrinkage, that's the red. Again, shrinkage contributes the most. Then you have the creep, the green is the pre-stress effects, and the light blue is the dead load effects. So telling you what contributions are being made from different time-dependent phenomena. If you look at the ultimate base shear, and that's shown here from the analysis for all of the columns. So we have 37 columns from all 8 structures. And then this is again showing the percentage of contribution from different time-dependent effects. And again, you can see now that the creep plays a noticeable influence along with the shrinkage strains. Now in this figure, we are comparing the estimated displacement of the columns using a simplified, the 3 approaches that we have done along with what we call the current practice, which is the one we are evaluating right now with Cartrans. But if you focus on the approach 1, 2, and 3, as I said before, you should expect a good response or good results coming from the approach 2 because we are relying on the analysis outcomes from the finite element for each of the bridges for simple design calculations. And there's no surprise that they came out to be good. But what's interesting is that the method 1 is definitely confirming that that approach may actually provide you a satisfactory estimate of the displacement. And approach 3 will also provide satisfactory results, whether we rely on what we recommend as an average value or you use the estimated pre-stress by using some simpler approach to evaluate the pre-stress strain. If you go and look at in the next slide the forces, in other words, the base shear forces developed in these structures, and I have 4 different cases. Again, just focus on approach 1, 2, and 3. These are the simplified approaches that we are evaluating. We are expecting that approach 2 to produce the most accurate results. And you can see they're pretty good. There are some outliers you notice, and they did show up on the other figures as well, which we're evaluating to see why 1 or 2 points were outside. But for the most part, we're doing a pretty good job in terms of evaluating how much base shear one should, or how much base shear one should expect in these columns so that you can actually design these columns for more accurate value of the base shear.